Okay, so now continuing on with our lecture for Chapter 3 on probability theory, the next thing we're going to look at is known as the addition rule. The addition rule is used when we're looking for the probability of A or B. So if you're looking for A or B occurring, which means either A occurred or B occurred or both occurred, you think that you need to think about that you'll be adding those two probabilities together. The probability of both A and B means that both A and B occur at the same time. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of both A and B occurring. We're doing this subtraction because when we add up A and then we add up B, anything that has occurred in both A and B, we added it when we added A and we added it when we added B, so we need to subtract it out once. Now, a card is picked at random from a normal deck of cards. What's the probability that either the card is a 6 or a heart? Now remember, there are 4 6s in a normal 52 card deck. There are 13 hearts in a normal 52 card deck, and there is one card that is both a 6 and a heart. So pause the lecture for a minute and answer this question. All right, so remember, the probability of 6 was 4 out of 52, plus the probability of a heart was 13 out of 52, minus the 6 of hearts, which we counted here and here. So we don't want to count it twice, so we need to subtract it out once, so minus 1 out of 32, and we'll get 1 out of 52, and thus we get, when we reduce that fraction, we get 4 out of 13. Mutually exclusive events. Two events, A and B, are mutually exclusive if they cannot occur at the same time. If A is born in Tampa and B is born in New Orleans, there is no person that can have both A and B both occurring. So if both A and B equals 0, then that means that A and B are mutually exclusive because A and B cannot both occur. If there's a probability of 0.56 that it will rain today, what's the probability that it won't rain? Okay, we have covered the theory behind this question. Pause the lecture and think about the answer. Since it'll either rain or not rain, this is the complement rule. So 1 minus 0.56 is 0.44, the probability that it will not rain. So let's look at some notation. The probability of A and B means A occurs in the first trial and B occurs in the second trial. The probability of B with a straight up line is read given that A has occurred. So we're looking for the probability of A given that we know that event A has already occurred. Independent events. Two events are independent if the occurrence of one does not affect the occurrence of the other. So if A and B are independent of each other, then the probability of A, given that B has occurred, is just the probability of A. Otherwise, we say the events are dependent. Conditional probability. The probability of B occurring given that A has already occurred is denoted by the probability of B given that A has occurred is equal to the probability of A and B both occurring divided by the probability of A. For example, what's the probability of choosing a diamond given that you have a red card? By the formula, that's 13 out of 52 is the probability of choosing diamond divided by the probability of choosing a red card. 26 out of the 52 are red, so it's 1/2. By intuition, half of the red cards are diamonds, right? Suppose we want to say dogs have fleas, dogs do not have fleas, brown dogs and black dogs. What's the probability that a dog has fleas given that he's brown? So we're only interested in these 80 dogs here. Out of these 80 dogs, because it's given that the dog is brown, out of these 80 dogs, 35 have fleas. So 35 out of 80 is the probability that the dog has fleas given that he is brown. The multiplication rule is used for finding the probability of A and B. A happening and then B, so it's equal to the probability of A times the probability of B given that A has occurred. Now we know that A has occurred because if A did not occur, there's no way that we could get A and B both occurring. If A and B are independent, then the probability of B, given that A has occurred, is just equal to the probability of B. So if two events are independent, the probability of A and B is just equal to the probability of A times the probability of B. Now, in a standard deck of cards, what's the probability of choosing two cards without replacement? If I did not put a card back in after my first draw, these are not independent events because I have changed the probability of the second draw being a club. So pause the lecture for just a minute. See if you can answer this question using the multiplication rule. All right, so it would be the probability of the first club is 13 out of 52 times, as long as the first one was a club and it was not replaced, now I only have 12 clubs left in my deck and I only have 51 cards left in my deck. So multiply those two together and you get 3 out of 51. If I do replace, then these two events are independent because I put the card back, so it does not, my second draw is not affected by what happened on my first draw. So pause the lecture for just a minute and see if you can answer this question. It's 1 out of 16. Treating dependent events as independent. Now, it's common practice when drawing small samples from very, very large populations, then we don't treat, even without replacement, we do not treat them as dependent events. If you're drawing from a population of 1 million and you're not replacing the first one, it really doesn't matter. You really haven't changed. We can treat those as independent events. But if the sample size is less than 5% of the population, you may treat the selections as being independent. That's the end of Chapter 3. You can now go to the assigned problems in the textbook and try them. There is no mini-tab lab for Chapter 3, so that's the end. It's all the assignments in Chapter 3.